Welcome back, grade 7 and 8, to our next video dealing with light. Earlier in this unit, we learned that the sun is the most abundant source of light on Earth. However, there's far more to sunshine than just meets the eye. Besides the visible energy that we call light, the sun also radiates invisible energy. The light we can see is just a tiny band of a much broader spectrum. You may have seen how water waves can be used to represent how light moves through space. However, light is a very different kind of wave than those that travel through water. In a water wave, water particles vibrate up and down as the water passes through the water. But in a light wave, electrical and magnetic fields vibrate. As a result, light is classified as electromagnetic radiation. Visible light energy and all the invisible forms of radiation, all the invisible forms of radiant energy exist on this electromagnetic spectrum. And here we see an example of that. And there's a lot of interesting things on this diagram here. So first of all, we see that going from the left all the way to the right, that's the entire electromagnetic spectrum. We also see how it can be represented by different wavelengths. So we have very large wavelengths here at the beginning, and as we decrease our wavelengths or increase their frequency, we get different types of waves, everywhere from radio waves at the largest wavelengths, all the way down to gamma rays at the shortest one. And somewhere in the middle here is where we have our visible light, going from red all the way to violet. Different color of light represent different frequencies and wavelengths of light. So here we see going from red all the way down to violet that each different color is represented by a different wavelength in nanometers here. That's also represented by a different frequency in hertz. Remember, frequency is how fast it's vibrating or how quickly those waves are coming. And you'll see that as we go from red to violet, those wavelengths are decreasing, which means the frequency is increasing. The table shows the wavelength and frequency of the colors in the visible spectrum. And in the rest of this video, we're going to examine more closely the bands of invisible energy beyond just the red and violet ends of the light spectrum. So we've talked quite a bit about this visible light small piece here, but what about the rest? Well, that's what we're going to get into in a little bit. First, let's take a look at infrared. If you'll notice that infrared is where it goes just beyond, to the left here, red. So we have red, and then before that, we have infrared. Red light has wavelengths of about 700 nanometers. If you could stretch it out to 1,000 nanometers, it would become heat radiation, or infrared radiation. Your eyes would no longer see it, but your skin would be able to sense it. Because infrared radiation is heat radiation, anything that is warmer than its surroundings emits more infrared rays. Infrared radiation has many uses. Motion sensors, burglar alarms, and heat lamps all use this technology. Here we see how an infrared lamp is being used to warm a baby chick there as well. And what if we go before that? What if we go into an even longer wavelength? Well, then we get into what we call radio waves. Suppose you could stretch the infrared wave out again even further, so the wavelength becomes a few millimeters long. We would obtain radio waves. Radio waves have a longer wavelength and a lower frequency than visible light. Different types of radio waves have different uses. One of those is microwaves. Microwaves have the shortest wavelength and the highest frequency of all the radio waves. Microwave ovens, for example, use a specific wavelength or frequency of microwave that is strongly absorbed by water particles. And when the water particles in the food absorb microwaves, they begin to vibrate quickly and become hot. Only foods that contain water particles can be heated using microwaves. So this is interesting. If you've ever tried to put something in your microwave that doesn't actually have water particles in it, it's not going to heat up in the microwave. And that's because those microwaves are kind of tuned to be an exact frequency to be able to cause water particles to vibrate more vibrantly, or to vibrate more violently, or much more, thereby creating higher heat. Microwave frequencies are also used in telecommunication, as we can see here in this image. Microwaves can be transmitted to telecommunication satellites that orbit Earth. The satellites receive microwave signals, amplify them, and retransmit them to another location. Microwaves are also used in radar. In this case, microwaves are beamed through the air. The waves that reflect from an object tell the radar operator, tell the program that picks that up, the location and speed of the object. And we use this for all sorts of things. Air traffic controllers depend on radar to guide aircrafts through the air as well. Radio waves with longer wavelengths than radio waves have longer wavelengths than microwaves, and they're used to broadcast radio and even sometimes TV programs. Most radio waves are harmless. In fact, radio waves are streaming through the air even right now. Canada has even had an involvement in terms of radio waves and its use of it in order to take different satellite image pictures. We used to have a program or a satellite called RadarSat that was used for quite a long time to be able to take radar images of the entire world. It was used to monitor global changes in pattern, to monitor oil spills, environmental damage, and all of those sorts of things, and to send that information back to us. Canada still does have that technology, or is still using that, but they're using a newer upgraded model called the RadarSat 2. They also have a new version of the RadarSat just recently launched a couple of years ago that they're using to also help out with weather patterns and flooding as a better way to understand that. Okay, so that tells us a little bit more about the left side of visible light spectrum, the infrared and radio waves, as we go through to increasing wavelengths or decreasing frequencies. But now let's take a look at the opposite side. Just beyond the violet end, remember light goes from red to violet, just past violet, we get wavelengths of 200 nanometers or less are known as ultraviolet radiation. This radiation is very energetic and it causes tanning, which is the skin's way of trying to protect itself from the UV waves. Ultraviolet radiation can damage our cornea, the front surface of the eye. This can lead to a fogging of the cornea, causing a slow loss of vision. Sunglasses are usually helpful and used to block ultraviolet radiation and help to protect our cornea from damage. In recent years, more and more ultraviolet radiation from the sun has been reaching the surface of the Earth. That was due in part from a decrease in Earth's ozone layer, which since has changed significantly. Ozone, which we learned in our previous atmosphere unit, is a form of oxygen located in the Earth's atmosphere about 20 to 25 kilometers above the ground. When UV radiation from the sun reaches the atmosphere, ozone absorbs much of the UV radiation. This absorption prevents the UV light from reaching Earth's surface. And if you remember from our last unit as well, we even learned that there are different types of UV radiation, UVA, UVB, and UVC, that have different effects on us and have different effects with the atmosphere or interactions with the atmosphere. Some of you may have also researched that some of the different pollutants in our atmosphere, though, can be very damaging to the Earth's ozone layer. Some chemicals used in aerosol spray cans, for example, are able to rise through the atmosphere and break down the ozone particles that are trying to protect us from some of the more damaging versions of UV radiation. Freon is a gas once frequently used in refrigerators and air conditioners, and that can also destroy ozone particles. Fortunately, though, many spray products are now manufactured without ozone-destroying chemicals, and the use of freons has been banned in many different countries to try to prevent this from continuing to be an issue. Past ultraviolet, we now have X rays. At even shorter wavelengths and higher frequencies on the radiant energy spectrum are X rays. Or originally, actually, they were called Röntgen rays, and then later on switched with the name X rays, as X stands for our unknown in math, our variable in math. These waves are very penetrating and extremely energetic. X rays can actually pass easily through tissue such as skin and muscle. However, X rays are absorbed by bone. And we can see this in the picture here where we have an X-ray of, it looks like someone's hand with a broken bone in their arm. And we can see that because they're allowed to pass through the skin and they get absorbed, the radiation gets absorbed by the bones. People who work with X-rays protect themselves from harmful radiation by leaving the room while the equipment is being used. When a dentist takes an X-ray of your teeth, they might place a shielding pad on your body to protect you. The dentist then leaves the room before operating the X-ray machine. As we get to decreased wavelengths or increased frequencies, we start to get different energetic particles, and the more energetic these particles are, the more worried we have to be about their effects on our body. And that's why when we get an X-ray, yes, it is a risk to us, but it's an important thing that we need to do in order to fix an immediate major problem at the moment. But it's definitely not something that you want to do on a regular basis. Obviously, you probably shouldn't be breaking bones on a regular basis. Our very last section in our electromagnetic spectrum that we're going to take a look at briefly here is our gamma rays section. Gamma rays have the shortest wavelength and the highest energy of all the waves in the electromagnetic spectrum. Gamma rays result from nuclear reactions and can actually kill cells. However, sometimes the ability to destroy cells is actually useful. For example, when doctors discover a cancerous tumor in a patient's body, they might decide to destroy the tumor with gamma rays, and this is known as radiation therapy. So if you've ever heard of somebody, or maybe you've had somebody in your family who's had to go through radiation therapy, what they're doing is they're using these very, very strong gamma rays in order to kill cells, with the idea being that you are specifically targeting or killing the cancerous damaging cells in someone's body. As we've learned, visible light represents only a small part of the electromagnetic spectrum. We are surrounded by energy waves. However, many of these waves are invisible. They exist in frequencies we cannot see. Nonetheless, these invisible waves serve important roles, from transmitting music to our homes to saving lives in hospitals.